Okay, this will be a short one, but it's tidying up chapter 9. So if you do your test for serial correlation, and again, this is not necessarily the most popular test, but it was the much easier one to explain, and also he didn't have the tables for the other test in the book. But honestly, nowadays with the internet, a lot of this stuff is easy to look up and work out. If you did end up doing this as part of your job and you became quite familiar with it, I think you could teach yourself the other tests. But I want you to have the basic background of what's going on and what's being tested for. All right. So let's say you ran the Durbin-Watson thing and you ended up with a number below that lower limit, so you had to reject the null hypothesis of no serial correlation. Well, now you got a problem. What's the first thing you do? Double check to make sure it's not impure. Make sure you haven't misspecified your regression, that you haven't put the wrong functional form. That's the very first thing you got to do. Now, when you're convinced, oh no, I think the regression's okay, I got a problem. Now you got a couple of choices. One is called generalized least squares, all right? And it gets rid of the first order serial correlation, and the way it does it, here, I'll show you. It's not that complicated. Again, the computer does it for you. But let's say you have, yeah. All right, yt equals beta sub 0 plus beta sub 1 x sub t, plus error term sub t, where that error term is really correlated with the previous error term, which of course is the problem, right? So in the next, so let's rewrite this. We've decided that is statistically significant positive value here if we have positive serial correlation. Oh, I forgot the row, sorry. Let's see. Rho e sub t minus 1. Yeah. All right. Now, check out this equation. Take the previous equation. Let me write this in a different color. Take this equation. Yeah, I'll do it this way. All right. Multiply by rho and lag 1 period. So this is going to be drawn from the first equation, not from this. I'm not manipulating the second one. We've gotten this far. All we've done is substituted in the rho et minus 1 plus the random error term for that et. So this is the proper form, or the more explicit form, if you will, that's showing the actual first degree serial correlation, first order rather. And so down here, I'm going to do something completely different. And so all I'm going to do is I'm going to multiply this equation through by rho. You want to do it that way or that way? Yeah. Oh, I forgot my minus 1. All right. I multiplied everything through by rho, which if I'm multiplying both sides by rho, no problem, right? And then I lagged everything one time period. But let's say it was for the time period before time period t, which is also perfectly legal. Then, see, I was going to point something out about this. Okay, oh, by the way, so I don't have a subscript on this, obviously. It's a constant, all right? So we don't have to subscript that. Now, I want to subtract the red equation from the blue equation that's right before it. Yeah, I want to subtract. In fact, let me make up a new notation that doesn't really exist in mathematics. Minus, all right? So I'm going to subtract this from that. What would you get? You would get yt minus rho yt minus 1 is equal to, let's see, beta sub 0 minus rho beta sub 0. Okay, already got that? Yeah, okay. Plus beta 1 xt minus rho beta 1 xt. Yeah, that's right. plus E sub t minus rho E sub t minus 1. Okay, and let me kind of put in parentheses each one of those new terms. Is that right? Yeah. Okay. First cool thing to check out. Look at that last term. And then look back at this equation. What would ET minus rho ET minus 1 be equal to? A random error term. In other words, this right here gets rid of the first order serial correlation, right? E sub t minus rho E sub t minus 1 gets rid of the serial correlation. Now we just have a random error term. Now what have we got in the rest of the regression here? Now let me, over here, yeah. It just says to rewrite the equation like this. I don't know if I want to do it that way though. Yeah, okay. All right. The computer can easily estimate a row because what you do is you run the regression once, and then of course you've run the Durbin-Watson, right? And so the Durbin-Watson had to estimate a row. So all you got to do now is, and it will do it for you. I assume, I haven't done generalized least squares in Stata, but I assume it will do it for you. But and if not, you do a couple of generate statements. Now what you want to do is you want to multiply a lagged version of the dependent variable by row and subtract it from y sub t. So this is sort of this y sub t here is that. So you've done this generate statement, you've created a new dependent variable. Here, I mean, honestly, we don't really care that much about the intercept. Beta sub 0 times 1 minus rho. That's what it ends up being. But again, there's a lot of reasons not to pay much attention to the intercept. Then beta sub 1, and this is going to be x sub t star. And sorry, let me move this over a little bit. And let me show you where I got this term right here. And then we're just about done, aren't we? Yeah. Let me show you where I got this. Over here. You see that? Yes, if I get out of the way, you can see it. All right, remember that middle term over here? It was beta sub 1 x sub t minus rho beta sub 1 x sub t. Well, let's factor beta sub 1 out of there. So this is what the new x star is, and here's the really important thing. This is the original beta. This beta sub 1 here is exactly what you were after initially. We didn't have to do any, it's like, oh, well, the beta sub 1 we've got now really isn't exactly what this would have been up here had there been no serial correlation. No, it is. It's the same beta sub 1. So we can estimate beta sub 1. We've got a weird variable here for x, which we had to go through and take each x and subtract from it rho times the previous observation. We've lost a degree of freedom because we lost we lose one observation because each observation now is itself minus its previous one. Well, the very first observation doesn't have a previous one, so you lose that one forever. But it's the original beta sub 0. You get something weird for beta sub 1. You get something weird for beta sub 0. Although you could still calculate it, you could still figure out what it would be. But remember, we don't really care that much about it anyway. But that's just the original beta sub 1. So generalized least squares can solve this problem for us of serial correlation. The next method is Newey-West standard errors. I have never done that, all right? And one of the glorious things about teaching a class is that you can skip over stuff you don't really care about. I don't really care about it. So, if in your literature search you find that you need to know how to do that, it's covered in the book. And then something that they didn't talk about in this chapter that they had in previous editions, and I'm not sure why, because it's a very good idea. There's something else you can do here too. It is very common to discover, erase all this, it is very common to discover that, okay, let me use my regression I've been telling you about. Investment is beta sub 0 plus beta sub 1, the forecast plus beta sub 2. I'm just going to do one of the surprise variables. I'm not going to write the rest of them out. It's not unusual to discover that if this is serially correlated, this is not. Change in investment. And we're actually going to come up again here in chapter 12 talking about an issue related to this. And I oftentimes end up doing this, I don't want to deal with serial correlation. And change is harder to explain than level. And that's why you saw the adjusted R-squares being around like 0.17 and so forth, is because I was measuring the change, which is much more difficult to explain. But it gets rid of the problem of serial correlation. Right? So I prefer to do that. So you can also difference. And what is change? And notice here how similar that is to the generalized least squares, but we're not multiplying by a row. And that often gets rid of it just by itself. All right, I think that's it. Oh, and I do want to mention, I do want to emphasize here, we're going to come up against another really important issue that is related to time series studies in chapter 12. I'm going to do my video on chapter 10, and then chapter 12 comes up, and where is it here? We need to figure out if these data series are stationary, all right? So, but that's a whole other issue, but it's a very important one for time series, so we'll revisit that. Well, no, not revisit it. We'll visit it for the first time later.